Hello, everybody. So what we're going to be looking at today is section 5.1. So section 5.1 means we're in a new chapter, means we're covering an entirely new topic. That's actually really good for us because since we are covering an entirely new topic, um, that means we get to start out easy. So that's always good. So in chapter 5, what chapter 5 is going to be about is it's going to be all about multiple integration. And yeah, so multiple integration. Now, the good thing about multiple integration is that the way you do multiple integration is you just do regular integrals. So you already know everything you need to know. You can do, well, you would have to know what the point was, but if you did know what the point was, you could go 5 sections ahead from where we are now and do a problem. Like I could explain how to do it in 2 minutes, and you could do a problem from 5 sections away, and you would actually be able to do it, um, provided you know how to do integrals at all. Um, but we have to go through and learn some of the theory for this. So that's where we will start today. So we're in section 5.1, which is going to be double integrals over rectangular regions. So what we're going to do is we're going to learn to recognize when a function is integrable. That just means when we can integrate it. Um, we're going to learn some of the properties of double integrals. We're going to learn to evaluate double integrals, and we're going to learn how to calculate a couple of simple things with a double integral, an area or like a volume. It's actually very straightforward, and yeah, so let's go ahead and get started. So where we want to start here is just kind of background. Um, so we're going to be doing this over a rectangular region. So um, a rectangular region is usually given like this region in R2 is, given by something like this, like X is between two numbers A and B, and then you have um, Y, which is also in between two numbers C and D. And then so if you're just looking at it in an XY plane, um, you just have a rectangle. I should have drawn the entire rectangle, but I didn't. So now I have to draw all 4 lines, right? So you just have an A and you have a B and you have a C and you have a D. And then your region R is the region that's in there. So just like that. So, ooh, that's not what I wanted. So that's a rectangular region, R in the XY plane, right? So that's very simple. They do a little bit more here. I don't really know um, why. They like to list R this way in your book. They say R R is going to be. They say A cross B. Sorry, interval A to B cross C to D. That's not a cross product. That's a Cartesian product. And what that means is basically what we already wrote. It's the set of all x comma y such that, you can say in R2, such that x is between A and B and y is in between C and D. So that's really just what we said, but they use that extra notation here, this kind of notation, to indicate a rectangle. And that's called, like, this is what the definition of a Cartesian product is. A Cartesian product is an ordered pair, and where you get the first element from the first set, get the second element, the second set. And so this is called a Cartesian product. It's a set operation, and we're using it here to give you an ordered pair that's enough. it's a set operation. They give you an ordered pair. I'm not going to like describe it in too much detail because like literally this is the definition of it right here. So there it is. So that's a rectangular region. So that's a lot of talking just to explain what a rectangle is, but I think you guys get it. Rectangle, the square looking thing, but not a square. Okay, so what we want to do from there is we want to figure out what this integral sort of thing is. So we're going to move on to, we're going to look at a, what are we going to call it? A double integral. That's letters. English letters are difficult for me. Okay, double integrals. So recall the idea of a Riemann sum. If you can, that'll be helpful. A Riemann sum from Calc 1, right? So the way we did this was we would, in Calculus 1, this is Calculus 1 definition, and it's not really a definition because we're skipping most of the definition. But if you had like you wanted to do an integral from a to b, and before you could calculate that integral, what we did was we divided this up into sections from a to b, and you drew these rectangles here like this. And then what we would say about those rectangles, if I can just color them in real quick. Beautiful. What we would say is that the area under the curve, let's say y equals f of x, for x between a and b, is approximately, right? We could say that the area is approximately the sum of the area of those rectangles. And what we did is we said every rectangle has the same width, let's say delta x. And then in order to get the heights of each rectangle, what you had to do is you had to pick some x values, right? Like maybe this one's x0 and maybe this one's x1, and then, you know, so on until you get to the end one, which is xn. And so if you come up here, actually, yeah, if you come up here, then you have these points on the curve, right? And so like this one here would be f of x, I guess it would be n minus 1, because I drew xn as the one on the end. So the one previous is n minus 1 up there. This first one would have been f of x0, for example. And those are how you calculate the heights of those rectangles. And so you would have f of xi, and if you multiplied the height of each rectangle by the width of each rectangle, you're calculating an area. And then if you add them all up from 1 to, I guess, 1 to n, then you would have the approximate area under that curve. And then what we did from there is if we just somehow said that we were going to let n go to infinity, which involves some other stuff going on, like, for example, the delta x ends up having to go to 0, because the width of each rectangle is getting smaller and smaller, then we would say that the area, it was exactly equal to that limit as n goes to infinity of this sum. And then we just made up the idea that this is what we were going to call the integral from a to b of f of x dx. And of course, there's things in the formula here, like the delta x, we changed to a dx, and the f of xi, we ended up writing f of x in the formula for the definite integral. Okay, and obviously that was not a rigorous definition, but hopefully what we did was remind you of what that Riemann sum stuff looked like, right? So what we're going to do is we're going to do the exact same thing for double integrals, although I will tell you right now, we're not going to do it in too much detail. So slightly more detail than we just did what we just did. So here's the thing. So consider, first of all, an f of x, y, z equals f of x, y maybe, that is, continuous on a rectangle R. And let R be, that A, B, C, D. So really the reason they use this kind of notation is this is quicker to write, slightly quicker to write than maybe, something like this. Not really that much quicker, but a little bit quicker. And it's easy to see that that's a rectangle. Okay, so we've got a function that's continuous, a rectangle function of two variables. Okay, and then what we're going to do is let's look at our rectangle. So let's say A, B, C, D. Oh, come on. We can make a better rectangle. Okay. So we got our rectangle here, right? And then what we're going to do is we're going to chop that rectangle up in pieces, just like we chopped the interval up here into pieces. So like here you had A, and then we chopped that up into a certain number of pieces. We're going to chop them into, it looks like the X is going to be chopped into M pieces. So like we're going to chop this up here into pieces. So like, let's call that like X1, X2, dot, dot, dot. And the last one will be, I guess I can call it BXM. And this is X0. So you chop the X interval into M pieces. So we cut A X less than X less than B into M subintervals. And again, we're not, I'm not doing too much with this. So like, you're not going to be like responsible for doing anything really with these definitions, I hope. So it doesn't matter really if it makes 100% sense. Just we want to get the general gist of this. So we cut A less than X less than B into M subintervals. The width, by the way, would be as follows. The width of each is delta X, and it would be B minus A over M. Same thing you do when you're doing regular integrals. Okay. Now, if I do the same thing for the C to D interval, we're going to cut A less than, nope, move. I hate it when notifications come down and they're like in the way and I can't click on what I need to click on. All right, so cut C less than Y less than D into, we'll say, N subintervals. The widths are delta Y going to be D minus C over N in that case. So we're cutting this up into a certain number of intervals as well. So this would be, I guess, Y0. This would be Y yn, and then, Y1, Y2, etc. Now what happens then is you actually are dividing this entire thing now into a whole lot of little squares. I thought my rectangle was on the lines, and it is not. Oh well, it's still better than I would have been able to draw by hand. Okay, so when you do that, you've divided R into a bunch of little smaller rectangles. They're not squares. They look like squares, but they're not necessarily squares. So this divides R into a whole bunch of little rectangles. Okay. All right. Now, from there, what if we pick one point inside each rectangle? Now, what point do you choose? It doesn't matter. We're just like, you're just going to these rectangles and you just choose one. They don't have to be in the middle. They could be in the middle, but they don't have to be in the middle. Probably didn't need to do this many, but we did. Okay. So we choose one point in each one here. Okay. And yes. And so each of those points can be referred to in a certain way. We could say choose one point inside each rectangle. Let's call those points each point, or call the points like xij, comma yij, where um, the ij refers to the location basically of the rectangle. Ij tells you which box you are in, right? So like for example, if you took one in particular, like if I say like what's this one right here, right? You have that point right there, and then that would be well, it's one, two, three, four, fourth box, and then one up, right? So that would be like the X, like four one, for example. So it doesn't really matter. Again, we're not being super rigorous here. So that's what we're doing. Also, they did a weird thing here. They put asterisks over them. That's how they labeled them. Don't know why. It doesn't matter. Okay. Now, um, what this does is if you look, like if you have a surface in 3D, I have a better drawing than what I'm about to do, so but I will copy paste it in a second. So here's what's happening. So you've got this like rectangle down here on the plane, and it's been divided into a bunch of sections, and you pick one point in each one, and you come up here on the curve, and there's a point on the curve. And if you take that point and you make a little box like right above the box, you can, not this way because it's too ugly, but what you've got going on there is this kind of thing. So you've got the dot down here, that's your xij, and then you come up here, you're getting that height from the surface, and so this height is going to be, or this point is going to be xij, yij, and then in order to get the height, you use the function like that. So this is yij. Okay, so you can make, this is the equivalent of one of these rectangles. These are rectangles, but we're in 3D space now. And so above each rectangle, you get one of these rectangular prisms here, a box. Okay, so so for each xij, yij, don't ask me why we have asterisks, you can make a box. um, by getting the height for the box from the function. So like Zij would be f of I x ij y ij, and that's it. And there's asterisks there again for some reason. All right. And so that's what we drew. That's what these boxes, that's what these, like one rectangle is here. Okay. Now, when you do all that, what's it look like? So let me get the picture, which I have. Good picture somewhere. I will find it. Should be in there. Yeah, this one. This one's good. Okay. So here's a better picture of what I was doing. So you find this little box, which here's a much better picture of that. And then for one of these boxes, right, you have a width here and a width here, delta y and delta x. And then you get the height from the function value. And then you get this picture of a whole bunch of boxes that are approximating this volume here. Okay, so what we get is if we add up the volume of all the boxes, okay, if we add up the volume of all of the boxes, we get that the volume under z equals f of x, y, and above the region R is equal to, or sorry, it's approximately equal to, well, how would you do that? You would need to add up the volume of all of these boxes, right? So each of these boxes has a volume, delta x, delta y, ij, ij. So that's like the width, the width here and the width here, and then they have a height, and the height is given by the f, right? Xij, Yij. And if we just make these constant, say they all have the same width, then you have this. So that's one box, but we have to sum over all of the boxes. And the thing is that since we did our x and our y separately, they make two sums, and they say, well, the I was for the x, so that was going from 1 to m, and then the j was going from 1 to n because we had n boxes in the y direction. And it actually doesn't matter which order you do this in. So that's it. So you have like m box or n intervals that way, and you have n intervals that way. And in order to sum over all of your boxes, you've got to sum over all of the i's and all of the j's. And this would be the volume of a single box. Okay. Now, just like before, we're just going to say, well, by magic, because I'm not going to prove it, let's just suppose that we just let the limit of m and n go to infinity for both of them. So we let m go to infinity and n go to infinity. And then what happens is these boxes get smaller and smaller, and then the volume will become perfect. So you get that the volume under z equals f of x, y, and above the region R is going to be exactly equal to that limit. You can write limit n goes to infinity, limit m goes to infinity, this thing, and we're going to do exactly what we did for the Riemann sums. So for the Riemann sums, what we did is we said, oh, well, when we take the limit of this sum, we just magically turn it into an integral, and that's the definition of the integral. Same thing here. We take the limits of these sums and this is going to magically turn into what we're calling the integral. So this is going to be an integral this way. So we write it two integral symbols next to each other. That indicates it's a double integral. The region was called R. That's the equivalent of a to b. And then the thing we're integrating was this function, f of xy. And then you have this delta x, delta y, which you either is going to be a dx or a dy, but that's less usual. In this form right here that I'm showing you, this is usually dA. And so you usually will see it written this way. Double integral over r, f of xy, dA. They kind of save the dx dy for slightly further away from where we are. Okay, so this is more commonly what you'll see at this point of what you're learning. Okay, and so this definition here, quote unquote definition, because it's not super rigorous, but this is the double integral of f of xy over the rectangular region R in the xy plane. Okay. And let me just box this whole entire thing here. That's your definition. Okay. So that is the double integral here. This thing right here, or this thing right here. Okay, so that's the double integral. Now the thing is that probably what we don't want to do is spend too much time not calculating it, which is easy to do. Right? Like we could spend more time going like, well, let's say we don't know how to do double integrals. How would you do a double integral if you don't know how to do a double integral? And I wouldn't. So, I mean, what I would do is I would learn the right way to do them, and then I would just start doing them the right way. And so that's what we'll do straight away. So the next thing we want to learn is, I guess we could learn properties of them, and then we can learn the theorem that actually lets us calculate them. So let's do properties first. That's the order they do them in the textbook here. So properties of double integrals. And these are going to be the exact same properties that you know for integrals in general. The ones that we have anyway. So like, for example, so suppose f of xy and g of xy are integrable, integrable, grable. They're integrable over region R. I'm not going to say rectangular region R because we're going to have other regions soon in the next section. So this is true for those as well. Also suppose that S union T is going to be R. And what I'm doing there is like, let's say you have a rectangle and like that's R, right? So this whole thing is R. If you take this and you split it up and you call this side S and you call this side like T, so like I got, let me get some colors here. So like if this side is S, and this side is T, and the whole thing is R, then we're going to do something with that in the definition. Okay, so That's what we got. Oh, and we need little m and big M are real numbers. Right, you know how it goes whenever we're listing a bunch of properties. Okay, so let's see here. So here's our first property. So if you wanted to do the double integral over R of f plus g dA, guess what? You can split that integral up and you can just do the integral of f and the integral of g. So again, basic integral property, right? You split up the integrals and you do them like piece by piece here. If it's addition. Um, what else? Also, you can do that for minus, right? Like if I put a minus. All right, so that's a property. Another property is going to be if you have a double integral. Hey, they didn't do it. Okay, they did it wrong. Weird. Okay, so if you have a double integral and a constant times f of x y dA, guess what? That constant can come out. Again, same property from regular integrals, right? Um, Third thing, they say if R is equal to S union T, we already wrote that. But also they say and S intersect T is the empty set. They're saying they don't overlap, right? So like S and T, like S is here, T is here, but they don't overlap at all. Um, then if you do an integral over S, and then you do an integral over T, that's the same thing as if you did the integral over R. Because if you integrate over S and over T, right, S and T add up to the entire R. So simple. Okay. Another property. If 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 one of your functions is always bigger than the other function um, over the region, we don't care outside of the region. So if you have one function, so you have a big one and then you have a small one, right? Then, well, guess what? When you do the integral of f, it's going to be bigger than the integral of g, right? So integral of big function is bigger than integral of small function. And that's also the same property exists for regular integrals. Okay, so another thing you can do is if f of xy is in between these two numbers, little m and big M, then your integral is going to be between two things. And it's a little bit tricky. So I'm going to say it's MA and big MA, where A is the area of R. Okay. And okay, there's one more property to do, but I want to explain this one a little bit. So like, imagine you have like a little box on the ground, not a little, like not on the ground, but like in space here, like that. And like, let's say this height here is little n. That's a little n. Okay. Then let's say you come up here and you have like a much bigger function, not function, a bigger rectangle. Okay. And then like, let's say this height is the big M. Okay. Now, if your function, right, you have this function here that is supposed to be between the big M and the little m. So you have this tall box and you have this short box. And what we're saying is your function just like somehow just lives in here, right? So like your f of x, y is just in between those two boxes. Well, um, remember that the interpretation of this is that it's the volume under the surface. So MA is like the area or the volume of the big box, and little ma is like the volume of the small box. And then the integral is the area under this purple surface. So of course the volume under the purple surface is going to be smaller than the big box, but bigger than the small box here. Okay, and that's what's going on with that theorem there. And then our last property is going to be so if f of x, y is actually in two kind of parts. Like suppose that your function of x and y, there's a part that is just got x's in it, and there's a part that just has y's in it. And I'll show you an example of this. Um, and suppose that r is x comma y such that x is between a and b and y is in between c and d. Okay, that's your r. Then it turns out that if this is the scenario, then your integral for r of f of x, y dA can actually be split into two integrals. One integral from a to b of the function of x, and then one integral from c to d of the function of y. Okay? Um, so I think I don't want to explain that very much right now. Basically, what we're saying is like if part of it just has x's and part of it just has y's, then you're able to split this double integral into single integrals. And the reason I don't want to explain that too much now is because we're going to have a better we're going to learn how to do these anyway, and you're not really going to be relying on this theorem. Okay, so here's how we actually do it. So this is going to be what we do. Let's see here. Okay, yeah, I guess we'll do that. So then we're going to talk about computing or evaluating double integrals. All right. So first thing is going to be an iterated integral. So we're just going to say suppose a, b, c, d are all real numbers. And let's say r is a, b, c, d, Cartesian product, right? So we're just dealing with the rectangular region. Okay. So when you see an integral written this way, a to b, c to d, and then you've got a function here like this, f of x, y, dx, dy, then what that means is this. So you've got this integral in the middle, right? You've got this integral here. I wrote these in the wrong order. Fix this. Y and then x. You'll see y in a second. If you take this right here, the part that I highlighted looks like a complete integral, right? integral from c to d of f of x y dy. And that's actually what you do. You can actually perform that integral from c to d of f of x y dy, get a number there, and then after you get a number here, or whatever you get, well, it'll be a number. No, it'll have x's. Then you do the integral from a to b of whatever that result is, dx. Okay, so that's one iterated integral. The other way to do the iterated integral would be if these were the other way around. So you have the a to b on the inside. And so the reason the order matters here is because remember, so based on this, the x is between a and b, and the y is in between c and d, right? So if this is c and d, you got to have the y here. And if this is a and b, you've got to have the x here. The order matters here. So when you write this, it means the integral from c to d of the integral from a to b f of x y dx. And then after you're done with that integral, you do a separate integral dy. Now, this is just a definition of what we call iterated integrals. Okay, so these are called iterated integrals. That's not going to make a box, is it? No. Okay, so those are called iterated integrals. And they're called iterated integrals. Iterated means like 1, 2, 3, 4, doing a number of things in succession. So the iteration here is first you do the inside integral, then you do the outside integral. So you're doing two integrals in order, and those are iterations. First iteration, second iteration. Now, at this point in your book doesn't make you do one of these. I'm just going to do one just to show you what an iterated integral would look like. So like, let's say I go 5 to 6, and then let's say I go 0 to 2, and then let's say I go x squared, y squared, dy, dx. Okay, and I want to evaluate this. Okay, so the first thing to do would be to interpret it as a double integral, or sorry, as an iterated integral. So solution, right? So you have this integral from 5 to 6, and then parentheses 0 to 2, x squared, y squared, dy, dx, right? Now, what I just did here is just interpreting it according to these definitions, right? According to the first one. I just put the parentheses where the parentheses go, okay? Now, what you have to do here is you evaluate this integral inside first. So you evaluate this completely. And we're doing an integral with respect to y, so you're treating x like it's a constant. Since the integral is for y, you treat x like a constant, just like you do for partial derivatives, right? When you're doing a partial with respect to x, you just treat y like a constant. Same thing here. We're integrating with respect to y, so x is a constant. And actually, because x is a constant, you may as well, you don't have to, but if you want to, you can take that x and actually just move it outside that integral. You can just go, okay, well, that's going to be, might as well take that out. Right? That was a property. That was a property of integrals that we learned just a few minutes ago. So X can come out if it's a constant. It's a constant for the moment. So then we can do this integral here. So do this. Okay, so I have integral from 5 to 6. I've got that x squared. And then just how do you do this integral here, right? So this is a very simple integral. It's actually the integral of y squared dy. So that's y to the 3 over 3. So that's y to the 3 over 3. And then the limits of integration are 0 and 2. And then you've got this dx here on the end. So we integrated. Now you know how to integrate, right? You plug in your 2 and you plug in your 0. So I've got integral from 5 to 6, x squared. You put the 2 in here, you get 2 to the 3 over 3 minus 0 to the 3 over 3. And then a dx. You work that out in the parentheses there, that's going to be 8/3. And now I've got a second integral to do. Now work out the other integral. And that integral is not going to be like super hard to do or anything. So I could take I could actually take the 8/3 out, right? Using a rule for integrals. And we're integrating from 5 to 6 of x squared dx. So that's a pretty easy integral. X to the 3 over 3 from 5 to 6. So that's 8/3. 6 to the 3 over 3 minus 5 to the 3 over 3. I need a calculator for that. I don't know what 6 to the 3 is. So I got 6 to the 3 minus, over 3 minus 5 to the 3 over 3, which is 30 and a third, or 91/3. So this is 8/3 times 91/3, which is 728 over 9. And that would be the answer for this integral. So it's an iterated integral. So really you're just integrating twice, once for y and then once for x. And you just do them in the order that they're written. So when you see dy first, that means you're going to do this inside integral and it's a y integral. And when you're done, you're going to do the outside integral, and the outside integral is an x integral. So the order there matters on those. Okay, so that's an iterated integral. Now, why do we care about iterated integrals? The reason we care about them is we have a theorem called Fubinis Theorem. Now, Fubini is a made-up name. That's not true. But it sounds like a made-up name, right? Who would name their kid Fubini? Probably gets beat up all the time. All right, so here's Fubini's theorem. So let R equal, let's just say A, B, C, D, right? Rectangular region. And then needs to be continuous. So let f of x, y be continuous over R. Okay. Then here it is. Here's the punchline. The double integral of f of x, y dA, that was in our definition of what a double integral is, can be calculated as, well, the double integral over R, f of x, y dx, dy. Of course, we know that because dx, dy was what we had to start with when I did it. But it's actually an iterated integral. So you can either go c to d a to b, c to d of f of x, y, and then I guess that would be dy dx. Or you can reverse the order, your choice, f of x, y, dx, dy. So what this is saying, so that's the theorem here. And so what this is saying is when you have a double integral, you just do an iterated integral instead. So that's all we're saying here. So Fubinis theorem says that you compute double integrals over R by an iterated integral. And you even have a choice of which one that you want to use. Okay, so that's what Fubinis theorem says. And I'm not going to prove that. We're just going to write it there. So let's see here. We've already done one iterated integral here. Let's, oh, they're very sneaky here. Okay. So I'm going to go to the homework. I'm going to pick one out of the homework. Where is the homework? There it is. Oh, no, that's not it. There it is. Oh, Fubinis. Next. Preview. Come on. Oh, I did this wrong. Never hit next in Canvas. It's always a lie. Trick. Are you kidding me? That's all? Oh, no, it's not. It's not. It's not integration by parts. I keep thinking everything is integration by parts, but the variables are different, so it's not. Okay, so this is straight off the homework. So they even say use Fubinis theorem. It's fun to say, fun to do. Use Fubinis theorem to find double integral over R of f of x, y, dA. So like this notation here, like this is how you write a double integral, but this is not how you do a double integral, right? Like you put the R down here, but there's no such thing. Like how do you do a double integral? You can't do a double integral. You do single integrals, but you do two of them. But this is called a double integral, but you don't do it. You do two single integrals instead of a double integral. Fubinis theorem says so. But they write it this way, even though that's not how you do it. All right, so use Fubinis theorem to find that double integral where f of xy equals 3x squared sine 7y, and r equals, and they're going this notation, xy, such that x is between 0 and 1, y is between pi over 2 and pi. Okay, so how would you do that? Must be impossible. No, it's gonna be just fine. You'll see. It's super easy. Super easy if you can do basic integrals. Actually, let me just remind you. I want to remind you of something. Depending on what you had for calculus 2, or 1, you may not. Come on now. You may not have. Stop it. Make a box. Thank you. That's all I want. Make bigger. Okay, so depending on who you had for calculus 1 or calculus 2, you may not like have learned them this way, but this is just kind of a reminder of a quicker way to do this. When you have an integral of like, let's say sine like a constant x, you could do integration with substitution, but you should not. What you should do is you should say, oh, well, the antiderivative of sine kx, the antiderivative of the sine function is the negative cosine function. And then you should say, well, what's the k do? you end up dividing by k. Don't do substitution, right? Substitution is not how you want to do these. Similarly, for all like anything like this, right? If you do the integral of cosine kx, you just say, well, the antiderivative of cosine is sine. And so on. If you have an integral of e to the kx, well, the antiderivative of e to the x is e to the x. What's the k do? Ends up in the denominator, right? And the reason it's always like that is because if you were going to take the derivative of this, if you take the derivative of e to the kx, you'd multiply by k because of the chain rule. And so that k would cancel out that k, and that's how you get back to here. Point is, don't do substitution on those, okay? And the reason I'm mentioning it is right here, 7y. Okay, so let's do this. So the whole point is you've got this double integral over r f of x y dA. Now for us, it's going to be a double integral of our function, which is 3x squared sine 7y. Now we got to decide, do you want to do the x integral first or do you want to do the y integral first? And it doesn't really matter. We could just let's do the x integral first, but it doesn't really matter. So if you do the x integral first, your bounds for x are 0 and 1. So those go there. I wrote dx dx, didn't I? Oops. Dx dy. And then your bounds for y are pi over 2 and pi. So just make sure you match them up, right? The y is second and the x is first because of the way that I wrote it. Okay. Now, if I'm going to do this integral now, I know that basically this pi over 2 to pi integral is just out of the way. And I really just need to do the integral from 0 to 1 of 3x squared sine 7y dx first, and then this dy integral is separate afterwards. Now, you can formally take this out if you want, because we're doing the x integral and that's got y's only, but you don't have to, okay? You can just leave it there as a constant. So it's kind of your choice, where we could write it this way, integral from pi over 2 to pi and sine 7y, and then the integral 0 to 1, 3x squared dx, like this. You could do that. You could even use that, like, I think, sixth property from our list of properties, where you could actually separate it out and do two separate integrals completely, because like once you have it at this point, I did it again, man. So why? Like once you have at this point where you take the sign and move it out, you got this dy here, you can move the dy over there, and then this integral and this integral are just completely separate. That's that property 6. I'm actually not going to do that. So I won't do that. But you can. What I want to do instead is just kind of show you what I would normally do. And this is just how I prefer to write things. I don't know. I know I've had professors write things where they pull it out. So like for me, this is what I would do. So I would just go pi over 2 to pi. I'm just carrying that along. And when I do this integral on the inside here, I would simply do this. I would say, okay, well, the antiderivative of 3x squared is going to be just x cubed, right? Simple antiderivative. And if we're treating the sine 7y as a constant, then I can just leave it there, right? So I could have pulled it out of the integral, but also I can just leave it there. It's fine where it is as long as I know to treat it like a constant, okay? So you don't have to, pull it out if you don't want to. what am I doing? Oh yeah. So just remember to treat it like a constant for now, because it only has y's. So anyway, continuing on, what you're going to do, pi over 2 to pi, you need to plug your 0 and your 1 in for x, right? Remember what the variable was. So you end up with 1 cubed sine 7y minus 0 cubed sine 7y, if you do it this way, like that. Of course, that entire second term is going to disappear because of the 0. So then you end up with pi over 2 to pi of just 1 cubed sine 7y, which is just sine 7y, like that. Now, of course, that's what you would have gotten if you had pulled out the 7y like that anyway. It's not gonna change anything. It's just how you feel like writing it. Now from here, this integral is going to be pretty easy as well. The antiderivative of sine 7y is negative cosine 7y over 7 from pi over 2 to pi. And then you got negative cosine 7 pi over 7 minus negative cosine 7 pi over 2 over 7. And we got to figure out what this is. So 7 pi is where pi is, right? Because it's an odd number. So 7 pi is where pi is. Cosine of pi is negative 1. So this is negative 1. So negative 1, which is 1. So 1/7 minus. And then 7 pi over 2, well, that's like 3.5 pi. So I don't know if it's where pi over 2 is or whether it's where 3 pi over 2 is, but it's an odd. And I know that then means it's going to be 0. So I think we do all this work and we get 1/7 for our answer here. I'm just going to type that in. Submit. Oh, wow, I got it right, yo. Yeah. So anyway, that was one of them. I think on the next one, I will just leave that in. So let's do another one. Oh, they just say set up the integral. Okay, well, no, it's too simple. I'm going to get another one off the homework here. Oh, you're killing me. Oh, that's just another set up the integral. Why would they do that? Okay. Evaluate. That's what I wanted. There's a lot of problems where like literally like the answer like is just to type this in. They make you type in the limits and the function and which variable comes first and second. So very simple. But that's not what we have. So we want to find double integral over r f of x y dA, right? They're going to see that, write that over and over, where f of x y is 8x plus 8xy squared plus 5y, and r, they write this way. So they're changing up the notation on you from problem to problem, 1 to 4, 0 to 1. And they even say to do the y integral first. So we will, not that it matters. All right, so double integral function 8x plus 8xy squared plus 5y. We're doing the y integral first because they said so, and then dx. And then your limits, well, if we're doing the y integral first, our limits are 0 to 1 on the inside, right? Those are the y limits. And then the x limits are 1 to 4. Okay, so we just do the inside integral first, right? Do that first. So you got your integral from 1 to 4, and then we integrate here from 0 to 1, and then we got a dx on the end. So we need an antiderivative here. So remember, Point is, treat all x functions like they're just constant. Okay? So when you integrate a constant, like what's the antiderivative? Like if you're doing an x integral, for example, what's the antiderivative of 8 dy? So 8 dx would be 8x, right? So here, I said 8 because I was looking at 8, sorry. But the point is this is a constant dy. When you integrate a constant dy, it just adds a y, right? Like I'm just saying like this. If you had this, your answer would be that, right? Plus a constant, right? So just because our constant is 8x doesn't change the rules. We're treating 8x like a constant, so we have to write it this way. Oopsie. Okay. Now, the next one actually has a y, so you've got 8x is a constant, and then the antiderivative of y squared is y cubed over 3. And then this one has a y. Antiderivative of 5y is going to be 5y squared over 2. So, this is a little bit confusing. Make sure that makes sense to you. After you do that, we're plugging in our 0 and 1. So plug in 0 and 1 for y. Quite easy to get mixed up about which variable you're doing. So we'll put in a 1. We have 8, 1. See, I already messed up. I have 8x1 because we're plugging in for y plus 8x1 cubed over 3 plus 5, 1 squared over 2 minus, and then we're plugging in zeros. And what happens on these a lot of times, you like seeing zeros because if you plug in a 0 for y, you're going to end up with just a 0 and a 0 and a 0 when you plug them in. So you like those. So I didn't write them out. So we end up with the integral from 1 to 4. Work out what's going on in those parentheses there. I have 8x times 1, which is 8x. I've got 1 cubed, which is 1, so 8x over 3. And then I've got 5 halves, like that. And then you got a bunch of zeros, which I don't need to write. And then we have an x integral. Now you can combine these if you want here, the 8x and the 8/3. You have to know what 8 plus 8/3 is. Since I do have a calculator here, I'm just gonna, 8 plus 8/3, and it tells me set 32 over 3. So since I have a calculator, I might as well. So we have the antiderivative, 32 over 3x plus 5 over 2. There's our integral. So once one integral is done, your life's a lot easier. So antiderivatives here, 32 over 3. And then we need x squared over 2, which will change that to a 6 down there. Plus antiderivative of 5 halves is 5 halves x from 1 to 4. Plug in 4, plug in 1. 32 over 6. Should have just worked that out, but I didn't. Plug in the 1, 32 over 6, 1 squared plus 5 halves times 1. All right, what do we get? So, okay, 32, I'm just using calculator. 32 over 6 times 4 squared, which is times 16, plus 5 over 2 times 4, 95 and a third, which is 286 over 3 minus, what do we have here? 32 over 6, which I'll write 16/3 plus 5 halves. Actually, let's just do that. 16/3 plus 5 halves is 47 over 6. Just going to erase that and write 47 over 6. And then I've got 286 over 3 minus 47 over 6. And then the result is 87.5. So hopefully I typed that, or hopefully I haven't made a mistake. But nope, that's right. Okay, so that's good. Um, I'm gonna I hit next. I hit next instead of next question. Did it again. All right. So, what was I gonna say? Are you kidding me? Okay, we'll do that one. This will be our last one that we do because at this point we're just practicing integrals and reminding you of what to do. So this one just says evaluate, and it's an integral from -1 to 0, 1/2 to 1. Check this out. Sine inverse x plus 5 cosine inverse x dx dy. What is this? Okay. Okay. So if we're going to evaluate this, right? So solution, -1 to 0. And then, right, you got this whole y integral. But what we got to do is we got to find the antiderivatives of sine inverse and 5 cosine inverse x. And so, of course, we have, I posted them in the lecture notes for you. I'll link them again next to this, hopefully. But I'm on Paul's online notes. I'm going to look at his calculus cheat sheets. I'm going to find his common derivatives and integrals sheet. And I'm going to look up these antiderivatives, right? Because this is probably what you would do as well. So these are the antiderivatives of the inverse trig functions, which we will find somewhere. Oh, there they are. I see them. Haha. Can't believe he's making me do this. Okay. So there they are. So we can look them up right here. So we just have to look them up. So the antiderivative of sine inverse x, here it is, right here. I did not leave myself enough room. So it's going to be x sine inverse x plus square root 1 minus x squared. Okay. And then plus 5. And then I've got the antiderivative of cosine inverse, which is right here. Third one on the list. So that's going to be parentheses because the 5 needs to be on everything. Actually, I don't want a parentheses. So I'm going to put a 5 on everything. 5x cosine inverse x minus square root 1 minus x squared. Yikes. Is what it is. Okay, so that's your antiderivative. And I did mess up because I said I was going to remember to put 5 everywhere, and I didn't. So let me move that over. It was a minus, right? Hope so. Okay, so there's your antiderivative. Now, before you go on, we got to put in the 1 and put in the 1/2 here. So you put in the 1 into all of these. 1 sine inverse 1 plus square root 1 minus 1 squared. At least the square root's going to go away. Plus 5, 1 cosine inverse 1 minus 5 square root 1 minus 1 squared again. Minus, do the same thing, but with a 1/2. So 1/2 sine inverse 1/2 plus square root 1 minus 1/2 squared. I don't want parentheses there. Plus 5 1/2 cos inverse 1/2. I'm out of room. I'm going to write it down here. 5 square root 1 minus 1/2 squared. And then after you do all this, there's still a dy on the end. that we can't forget about. So this is yucky, but we're going to go through it. All right, so let's start here. What is sine inverse 1? Right? Where is the sine equal to 1? So the sine is equal to 1 at pi over 2. So that is pi over 2. All right, and then we got plus this thing, but that's 0. Plus, then you've got 5 cosine of 1. Cosine of 1 is 0, so this is going to be 5 times 0. That's nice. Minus, well, 1 minus 1 is 0 again, so that's minus 5 times 0. So it's actually not as bad as it looks. Then we got minus another big set of parentheses. This is going to be a little bit trickier. We have 1/2. Then you've got sine inverse of 1/2. So sine inverse of 1/2, where is the sine equal to 1/2? Pi over 6. Use a calculator if you need it on these. Okay, pi over 6 plus square root. What's in the square root? Well, 1/2 squared is 1/4. 1 minus 1/4 is 3/4. So this is, I said 3/4, but I wrote 3/2. So this is square root 3/4 plus 5 times 1/2. So that's 5/2. Cosine inverse of 1/2. Where is the cosine equal to 1/2? Cosine is equal to 1/2 at, oh, wait, hold on. I screwed up, didn't I? Wait, what am I doing? Oh, okay, no, I was momentarily confused here. I thought, for some reason, I thought I was about to do this wrong and then got confused. Okay, back here. 5 times 1/2 is 5/2. Cosine inverse of 1/2 is pi over 3, right? I think. Hope so. And then minus, we got 5 again, and then we got another square root of 3/4. Okay, and this is not done, right? This is not done when you do all this, because all of this is actually in parentheses, and then there's a dy at the end. Although I wonder if I did this in a bad way. Okay, let's simplify all this. So integral -1 to 0, and we're just going to add all this stuff up. So pi over 2 plus 0 plus 0 plus 0. Awesome. Pi over 2. Minus, and let's work out all this nonsense. We got a pi over 12, right? Pi over 12. Square root 3 over 4. If you square root the top and the bottom separately, you get square root 3 over 2 like that. Then you've got 5 pi over 6. And then we've got a 5 square root 3 over 2. And all of that's in parentheses, and then dy. Again, let's see if we can combine some like terms here. So what I'm going to do is anything with a pi in it, I'm going to add up. So I've got pi over 2, right? Pi over 2 minus pi over 12 minus pi over 12. Okay. And then plus 5 pi over 6. Oh, minus 5 pi over 6. And I get negative pi over 12. So I've got the integral from -1 to 0. Add up all my pi's, I get negative 5 over 12 pi. Now, if I add up the things that don't have pi, the only things that don't have pi are the root 3 over 2 and the 5 root 3 over 2. So root 3 over 2 plus 5 root 3 over 2 is going to be 6 root 3 over 2, right? Which is actually 3 root 3. So we end up with minus 3 root 3. Is that correct? Right? because add that to that will be 6 over 2, which is 3 root 3. I think that's correct, okay? I think that's correct. You know, who knows how many mistakes I just made in here. But here's where we end up with. Once we're here, we can actually do that second integral. So now integrate with respect to y. But guess what? There are no y's. So that means that when you integrate here, you're just going to basically get this constant, right? All of this is a constant here. 5 pi over 12 minus 3 root 3 y, and then evaluate that between -1 and 0. So put in the 0, and you're going to get, you know, nonsense times 0, minus, put in the -1, you're going to get negative 5 pi over 12 minus 3 root 3 times -1, which is going to be just simply negative 5 pi over 12 minus 3 root 3. And I'm just going to check this real quick because I think I made a sign error on something. I did. Let me fix it. So right here I got a minus and I changed it into a plus. Let me fix that. So that was supposed to be a minus, which means when you add these up, actually what happens is you have negative 5 root 3 over 2 plus root 3 over 2. So you get negative 4 root 3 over 2, which is negative 4. Ooh, I just erased stuff. Negative 4 root 3 over 2, but then with a minus. So actually should be a plus and a 2, which means that should be a plus and a 2, which means this should be a plus and a 2, which means this should be a plus and a 2. Okay. And that looks correct to me now. So that's the answer. Okay. So, I mean, hopefully you see that, you know, you can have pretty tough problems, but they're tough because integrals are tough, not because of anything new that you learned really. Basically you're just doing you're doing antiderivatives, treating one variable like a constant, which you already are familiar with. So I think that's it for now. Good luck on this. Yeah, and I think that's it for now. We're going to be doing a lot of these. This entire chapter is doing integrals like this for different purposes. Actually, hold on. I lied. I was going to stop the video and I changed my mind. So what we're actually going to do here is continue on just with one small bit of stuff here. So the last thing I wanted to do was just the last thing in the section, which is going to be just comments. So recall, or just remember, the double integral over R of f of x, y dA, that's just a general double integral, is the volume or net volume under the surface z equals f of x, y above the region R. That was by definition. So if they're asking you to calculate a volume, you do this. That's going to be provided that, you know, your function f of x, y is positive. Because if not, then there's no volume under it, right? It's a little bit different than that. And also, a second fact that we didn't cover, but if you do a double integral of just dA, then what you actually calculate is the area of R. Now, I'm just mentioning that you wouldn't do it for a rectangle because there's easier ways to calculate the area of a rectangle. So, you know, since R is a rectangle in this section, 5.1, you probably don't need an integral to compute the area Yeah, you probably don't need an integral to compute the area of a rectangle. Okay. But the reason I'm mentioning it specifically is because in the next section, R is not going to be a rectangle generally. And if we also scroll way back to the beginning of the notes here, they listed this in this section. They said use a double integral to compute an area or a volume. And well, you wouldn't use it to compute an area, not in this section, because the regions are rectangles, right? Length times width. Don't need an integral. Okay, so now I'm done. So hopefully that made some kind of sense. It's just integrals, but you get to practice your integrals here. Um, yeah, that's it for now, and I will talk to you guys next time.